we will be starting in a minute.
Okay.
Yeah. So I hope all of you have taken the quiz which we have floated yesterday, and we will be having one more quiz tomorrow evening. I will be sharing that another quiz. So I request every one of you to perform every one of the quiz, because we will be taking into consideration the quiz marks plus the attendance for the certification purpose. So I request all of you to please be active in the lectures. Tomorrow we'll be having very good lecture from C.T. Pilani, scientist. So that will be 4 hour session from 3 p.m. to 7 p.m. So I request you to attend that, so that especially in the research domain and especially in the teaching, you can correlate whatever you are teaching, what are the real applications of that. You can correlate that easily. So it is a good session from a CG scientist. Yeah, so I think we may start it now. Dr. Girdhar Gopal, you may please proceed.
Thank you, ma'am.
Welcome.
Uh, Good, good morning, everyone. I think all are the students and the UG and PG students. So we will start from
No,
basic and
we have, we have students plus faculty members and researchers. UG, PG students, faculty members and researchers from electrical, electronics and physics background we have.
yes.
Yeah, okay,
So
yes,
we
please.
start from basic, then we go to the advanced level. And here our topic is bistable multivibrator, monostable multivibrator, timers, and various non-linear wave forming circuits. Right. So what is multivibrator? The multivibrator is basically an electronic circuit that generates other non-sinusoidal signal like square wave, rectangular wave, sawtooth wave, ramp signal. These are known as the multivibrators. And what are the timers? Timer, they provide us some timing signals, and there are some other waveforming circuits like you want to generate some square wave, some and sinusoidal wave. So there are the different circuits, and here in this talk we will discuss different type of the circuit, how the multivibrator is very helpful in designing of electronic circuit and how it works as a switch, so that we can generate a square wave, right? So these are the content of my presentation, introduction, and for discussing the multivibrator, we will use op-amp. The multivibrator can be designed using the BJT and using operational amplifier and CMOS also. As as in the continuation of this program, because in the previous lecture you studied the op-amp, so I will discuss multivibrator using op-amp also, so that it can be helpful to understand the basic, right? And after that we will discuss timers and their applications and how we can use a 555 timer as a multivibrator, as stable multivibrator. So what is multivibrator? Multivibrator, as we as I already told, it is a simple electronic device, or you can say it is a switching circuit that can generate a non-sinusoidal, the non-sinusoidal waveform. Non-sinusoidal waveform. That is known as multivibrator. Why that term multivibrator? Multivibrator means multiple frequency, because when you see sinusoidal signal, suppose this is a sinusoidal signal. Suppose this is a sinusoidal signal. Suppose this is a sinusoidal signal. Suppose this signal is shifted by some amount, some phase shift. It is also shifted by some amount. It is also shifted by some amount. So these shifting represent a square wave. Shifting represent a square wave like this. This upper portion, this is lower portion. So the fact is that a square wave consists of larger number of the sinusoids of different frequency. That's why the name multivibrator means there are the multiple tone of sinusoidal signal in Fourier series representation that represent a square wave. So basically multivibrator work on the operation of positive feedback. It work on the positive feedback. So when we will design multivibrator using op-amp, then we will consider only the positive feedback only, right? Now there are the different modes of multivibrators. These modes are depending upon their stage. Here multivibrator are of consists of two stages, first stage and second stage. These stage may be BJT, these stage may be inverter, mean these stage may be diode. For example, when you consider or these stage may be a inverter also. When you consider when you take the odd number of the inverter, then it will wave as a ring oscillator, and or you can say it's a stable multivibrator, right? In this stage here we are here there are the two stages here. In this circuit operate in two states, and these stages are controlled by their circuit components, controlled by the circuit condition. Mean one, for example, when we talk about transistor, in case of the transistor there are two modes in a switching circuit. On represent a saturation and off represent a cutoff stage, right? And here we are considered the positive feedback only. This is the basic configuration of the multivibrator. Now there are the different types of multivibrator. One is a stable multivibrator, or you can say free running multivibrator, or oscillator. Monostable multivibrator, it is one short multivibrator, mean it consists only one stable state. And second state is the quasi-stable state. Quasi-stable state mean it is a semi-stable state, mean, or you can say it is a half-stable state. Now, how you can achieve this half-stable state? With the help of some external trigger. Mean when you apply external trigger, then your output goes to the quasi-stable state for a little period of time. Mean here time period is defined by their circuit component R and C, right? Now come to the bistable multivibrator. In case of the bistable multivibrator, as the name suggests, it has two stable states. And for switching of their state, for example, from V set to the minus V set, there are two states, plus V set to the minus V set. For switching of these states from V set to the minus V set, it required a external trigger. Means you can trigger here. There are the two pulses required. One pulse is to generate the half cycle of the square wave, and another pulse is used to generate the next half cycle of the square wave. Right. Now this is the pictorial configuration of the multivibrator. A stable multivibrator, there is no inputs, means it generates a pulse. Here the output then should be in the form of pulse. Monostable multivibrator, monostable means single shot, means it has only one stable state. It has only one stable state, and another stable quasi-stable state attained with the help of this trigger. In bistable multivibrator, there are the two pulses T1 and T2. That can be used to form a pulse, right? So this is the simple pictorial representation of different types of multivibrator, how they are distinct from each other. Right. Now come to their application. We are studying the multivibrator. Why we are studying? Because they have the numerous applications. A stable multivibrator, these are useful in designing the timing circuit, in delay circuit, and various transmission of the microwave signals. Monostable multivibrator, these are mainly used in the analog system to control the signal frequency. And bistable multivibrator, the most beautiful example of bistable multivibrator is the flip-flop that can be used as a frequency divider, counter, latches, and or you can say these are helpful in the designing of SRAM, memory storage unit, and content addressor memory. There are numerous applications of these multivibrator. Right. For understanding these bias multivibrator, let's revisit the op-amp. You have already studied the op-amp, but in a few minutes I will briefly summarize the op-amp. Op-amp, this is basically a direct couple amplifier having the high voltage gain. Right. Here it is the 741 pin IC, and in this there are the two inputs. When you see the internal schematic of the op-amp, you will find there is a differential amplifier. Based on that concept, here in case of the op-amp, the difference of the V1 and V2 is amplified with the help of this differential amplifier. Right. So there is one here, V1 is given to the positive terminal. This terminal is known as non-inverting, and V2 is given to the negative terminal. This terminal is known as inverting terminal. Right. Difference of these inputs, V1 minus V2, is known as VD, difference input signal. right? Since this op-amp is having no feedback, so gain we define as a open loop voltage gain. So what is the open loop voltage gain? Open loop voltage gain AOL is nothing but it is the output voltage V naught divided by VD. So we can write V naught is AOL into VD, and what is VD here? VD is the difference in the input voltage V1 and minus VD. Now come to the what is ideal op-amp. Ideally, op-amp is having the high voltage gain, mean approximately it is infinite, right? If VD is infinite, if VD is infinite, mean output voltage infinite. So output voltage is infinite. If VD is minus negative, then it will be V naught is minus infinite, because op-amp having the high voltage gain, approximately infinite. So output voltage of the op-amp is either in the range of plus infinite and minus infinite. However, gain of the op-amp is quite high, but output voltage never exceed the saturation voltage VCC and minus VE. Output voltage, practically op-amp gain is in the range of 10 to the power 6. So output voltage is either plus Vset or minus Vset, means it is plus VCC and minus VCC. Means most positive was output and most negative output. Right? Based on these characteristics, we draw the transfer characteristics. Transfer characteristic is the curve drawn between the output voltage versus input voltage. Here we are not talking about input voltage. This input voltage is the difference in input signal. So output voltage versus difference in input voltage. Here output is either plus Vset or minus Vset. So slope here, what is the slope here? Slope basically we define it change in output voltage to the change in input voltage. Here the change in input voltage is 0. I mean, there is no change here. So gain is infinite. This is the characteristic of ideal op-amp. Right? Practically gain is in the range of 10 to the power 6. So output voltage, it is open loop voltage multiplied by difference in input voltage, same circuit, and practically the saturation voltage is plus 15 voltage and minus 15 voltage. This is the practical transfer characteristics of the op-amp. This is very useful in designing of multi-vibrator. Why this is useful? Because here this characteristic divided two regions, linear region and the saturation region. Practically output voltage having two voltage, plus Vset and minus Vset. Right? So output voltage when you calculate this voltage, output input voltage, when you have to calculate input voltage is nothing but output voltage divided by gain. And output voltage, this is the output voltage divided by gain. So your input signal ranges from minus Vset to open loop voltage gain, minus Vset to the open loop voltage gain, plus Vset to the open loop voltage gain. And what is the range of output voltage? Minus Vset to the plus Vset. Right. So if this difference input is very small, in the range of minus Vset to AOL to the plus Vset to AOL, so the output voltage vary linearly in accordance with the difference input. Right? If this difference input is outside the range, then output voltage is saturated, means either it's plus Vset or minus Vset. Now, this saturation region, in this saturation region, this difference input. So based on these characteristics, I can conclude op-amp work in two regions, linear region and saturation region. When the op-amp is in this saturation region, or you can say when op-amp is without feedback, please note this line, when op-amp is without feedback or with positive feedback, then difference input is very large. Why in case of the positive feedback difference input is very large? Because in positive feedback input signal and the feedback signal are in same alignment, means their signal strength is boosted. So this difference input will be large. So op-amp will work in saturation region, right? So V naught is either plus Vset or minus Vset. But op-amp is without negative feedback, then negative feedback means difference input signal and the feedback signal are in opposite. So that signal strength is finally attenuated. So the feedback signal oppose the applied input. So we can say this is considered in the linear region. This negative feedback of op-amp is useful in the designing of integrator, differentiator, and many filters, or you can say different operation, different mathematical operation. This characteristics is helpful in the designing of multi-vibrators, and some non-linear waveform circuit like Square wave generator, right? And before understanding their we will understand the what is virtual short and what is virtual ground also. In virtual short, when the op-amp is in linear region mean the difference input is very small in the range of microvolt. Linear region mean this is the linear region. Here this in this linear region, difference input signal is very small in the range of microvolt. So the difference signal is very small. So mean small mean approximately is zero. Mean V1 minus V2 is 0. So V1 equal to V2. That means whatever the input signal you are applying at V1 or non-inverting terminal, same will appear at a V2. This is the criteria or this is the condition for virtual short. Right. Now what is virtual ground here? Same the application of the virtual short is the virtual ground. Mean if you have virtual short path is present in between node A and B, if one node is connected to ground, that means another node is also connected to ground also. This is the concept of virtual ground, right? Or there are you have understand the network analysis. There are different types of ground. Here we consider only this virtual ground only. The physical ground, AC ground means they have some path or resistance in the capacitance also. And virtual ground means virtually we are assuming that one terminal is one node is connected to ground, mean you have to approximate other node to the ground also, right? Now come to the application of op-amp. So based on the characteristics of the practical amplifier, op-amp are of two types: open loop op-amp or closed loop op-amp. Open loop means there is no feedback. Closed loop means there is a feedback. In case of open loop, op-amp work as a comparator. Right. In case of feedback may be of two types: positive feedback and negative feedback. The positive feedback is very interesting for us. Mean we have to understand this. Mean it can be useful in the designing of Schmitt trigger. Schmitt trigger, here the name Schmitt trigger, or you can say bistable multivibrator, waveform generator, sinusoidal oscillator. Or many applications of the negative feedback is amplifier or some mathematical operation. Right. So when we say op-amp is positive feedback means the difference input and feedback input are in same alignment. So the VD is greater means open loop voltage gain is also greater. So op-amp works in saturation region. So output is plus reset and minus reset. Here I have written same again because we have to understand this thing. This is very important for us. Bistable multivibrator. Now come to, so let's start from bistable multivibrator and slowly we prove the stable multivibrator. First thing, in a bistable multivibrator, as the name suggests, it has two states. So let's consider this circuit. This circuit is a bistable multivibrator using operational amplifier. Here in this circuit, there are the two resistance R1 and R2. These resistance R1 and R2 form a voltage divider networks. Now you can think in this way. There are the two resistance R1. This is the resistance R1. This is the resistance R2. Right. Here at this node there is a potential V0, and this connected to ground. Now this at this node there is a potential V1. This voltage divider network is very important for you because it form a positive feedback. So what if I have to calculate this V1 voltage? V1 voltage, the node voltage across this resistance R2. Now apply the voltage divider rule. V1 is nothing but it is the source voltage multiplied by R1 divided by R1 plus R2. But so V1 means the node voltage across this resistance. Sorry, this is R2. This is R2 and this is R1. So V1 voltage nothing but the voltage across the R1. So V0 multiplied by R1 divided by R1 plus R2. Now what is VD here? VD same concept. VD is nothing but it is V1 minus VI. Here VI is the input voltage. Because we have already told bistable multivibrator there are the two pulses you have to give to attain two stable states. So two pulses, one pulse is from V1, second is pulse from the VI. So that's why this is the external input signal VI we have given. Right.
Dr. Girdhar, just a minute. Yes. Can you just click on this arrow which is there near the settings? Double arrow is there near the settings in the Microsoft Edge, so it will take you to the full screen. Yeah. Thank you so much.
But no, it will not allow to write.
Just oh, okay, okay, yeah. Then you please continue in your original mode. Yes, yes. Thank you.
Slides are not visible, huh?
No, these are visible. Yeah, please tell.
Here, what is the difference in input signal? Vd is nothing but input signal at positive terminal minus input signal at negative terminal. So here, what is input signal at positive terminal? It is V1, and input signal at negative terminal, it is Vi. Now, by seeing, we can say it is positive feedback, but we have to understand logically and scientific way how it is positive feedback. How it is positive feedback? You can understand this as a, for example, if you increase, because it is bistable multivibrator, and the basic phenomena of bistable multivibrator is output voltage is either plus V set or minus V set. Correct? If you increase this output voltage, if you increase this output voltage, mean you, if you increase this output voltage, here, if you increase this output voltage, that means V1 will also increase. If this V1 is increased, means this VD is also increased. If this difference input signal VD is increased, since it is amplifier having high gain, so this output voltage is also increased. So so when you are increasing the output signal, mean ultimately you are having the output signal increase. Mean increment at one time, if the many time increment at on the other end, so it is positive feedback. This is the way to test the positive feedback. Right? So what? So increase in the output causes the further increase in the output. So we can say it is having the positive feedback. Or you can, so you can, so how much amount it will increase? I mean, you are increasing the V note, it will go to the V note in how much amount? It will go to the plus V set only. Same on the other hand, when you decrease this V note, on the other hand, when you decrease this V note, when you decrease this V note, same relationship, this V1 will decrease. If this V1 is decreasing, mean difference in input signal V1 minus Vi, it also decrease. So ultimately, this Vd decrease mean output voltage decrease. So how much amount it will decrease? Till V note becomes saturated, that is minus V set. So output voltage of V note is attained to value only, plus V set and the minus V set. So output voltage attain only two value, plus V set and the minus V set. So I have written here. So now you have relationship of V1 here. This is the relationship for V1. You have to remember in your mind. This is V1 is V naught R1 divided by R1 plus R2. Here V naught attain to value plus V set and minus V set. Depending upon this value, we are defining 2 points here. If V naught is plus V set, if V naught is plus V set, we define as upper point. If V naught minus V set, then we define the lower trigger point. So, or you can say this is upper threshold voltage or lower threshold voltage. So now we are finding this bistable multivibrator as a Schmidt trigger. So this is the circuit of Schmidt trigger. You can remember as a Schmidt trigger. In Schmidt trigger, now we are comparing the input signal with the V1, and so this circuit will convert input to the square wave output. So that's why we say it is a superior circuit also, right? Now let us consider two cases here. Let V naught is plus V set here. Let V naught is V set here, then V1 is upper trigger voltage. V set R1 divided by R1 plus R2. Now this input voltage is upper trigger voltage. Now this V1 Vi is compared with this upper trigger voltage. So what is the difference in voltage? Upper trigger voltage minus Vi. Now if this voltage, upper trigger voltage, if this voltage, suppose this is Vi, this is upper trigger voltage, if Vi is greater than upper trigger voltage, means it positive is greater than negative. That means difference, what is the difference here? But Vd is Vut minus Vi, right? If Vi is greater, if this is greater, means Vd will be smaller, difference will negative. So output changes from plus V set to minus V set. Now you can understand this as a graphically. That means if Vi, then now you are comparing this Vi with this upper trigger voltage, right? I am erasing this. Here, if Vi is less than Vut, that means if this Vi is less than Vut, means this Vd is positive. So output is plus V set. Output is plus V set, right? Now if Vi somewhat somehow Vi is greater than Vut, then Vd will become negative. So output switches from plus Vset to minus Vset. So this operation is repeated. So this operation will make a superior wave. That's why this circuit is known as steering circuit. Or you can say it is superior wave generator. Or you can say this is the application of bistable multivibrator or Schmitt trigger to form a superior wave. So now when the input is in increasing direction, here there is a transition from plus Vset to minus Vset. Now come to the second case when V naught is minus Vset, then V1 is low trigger voltage. Now you are comparing this V1 with the lower trigger voltage. So what is Vd here? Vd is the difference of low trigger voltage minus Vi. Now if Vi is greater than Vi is greater than lower trigger voltage, then this Vd is negative. Vd negative means output remain Vset. Output is Vset here. When the input voltage it is reduced, then it will be difference will be positive. So Vd is positive, so output, so there is a transition from minus Vset to plus Vset. So in both the cases you have generating the pulse. So these operations, when these two cases also form a stresses loop also. So here we defining two behavior. Whenever you are increasing the value of inputs and when you are having the decreasing value of the inputs, then there is a pulse here. Output have two values, plus Vset and minus Vset. Here on the study of these two cases only. Here you have to remember these two cases. Here I am writing this graph, right? When V1 is greater than Vut, there is transition from plus Vset to minus Vset. When Vi is less than Lut, there is a transition from minus Vset to the plus Vset. So this Schmitt trigger having a different behavior for increasing and decreasing value of the inputs. This property is known as hysteresis, and this difference upper trigger voltage and minus lower trigger voltage is known as hysteresis voltage, right? Depending upon the two cases, in two cases are represented in this graphical form, right? This is the difference of upper trigger voltage and minus lower trigger voltage. This is known as hysteresis bit or hysteresis voltage. So this is the pulse we have generated. You have given the input signal Vi. This is the input signal you have given, and pulse you have obtained. This pulse you have obtained, right? Output is plus Vset and minus Vset. If Vi is greater than VLT, mean low trigger voltage, difference is negative, output remain minus Vset, right? If Vi greater than Vut, difference, if Vi less than Vut, if Vi less than Vut, this difference is positive, so this it represents a plus Vset. So finally you have achieved the square wave. So this is the use of multivibrator. Now in previous discussion, we have connected this node as ground. Now somehow if you have given some reference voltage here, you are giving some reference voltage VR. Now can you find this voltage here by applying the superposition theorem? Here this voltage V1, can you find out by using the superposition theorem? Because there are the two source voltage here, V0 and VR. So by use of that source superposition theorem, what is V1 here? V1 is nothing but when you consider V0, V1 when you consider V0 only, you are considering only one source voltage V0. This is connected to ground. The source voltage is V0, and what is V1 here? At the time V1 is the voltage across R1. So V0 R1 by R1 plus R2. Now if you are considering the VR only, and this node is connected to ground, what is V1 here? V1 is not the voltage across the R1 only. Now V1 is the voltage across R2. So what is the voltage V1 here? Now this is VR, source voltage multiplied by R2 divided by R1 plus R2. Now in this case, now we know is either plus Vset or minus Vset. We can find upper trigger voltage and lower trigger voltage. So for this circuit, you can also define the hysteresis curve also. So we can finally conclude the bistable multivibrator. It converts any waveform to the square waveform, and it has two stable state only. That's why it's named as bistable circuit, and it's also known as regenerative comparator because of positive feedback. Right. Now come to the some problem we have we want to discuss on bistable multivibrator. Here I have given a bistable multivibrator based on this circuit. Based on this circuit, mean this voltage is reference voltage 4 voltage, and this is the output voltage. This is the VI, this is V1. Now you have to plot hysteresis loop, and now you have to calculate hysteresis width, and this is your target here, right? Now what should be the approach here? Approach is very simple. You have to find out this voltage, or you can remember the formula also. Mean you have to remember this formula. What is V1 here? V1 is nothing but V0 into this resistance R1 plus this resistance. Here this is the source voltage. This is the source voltage 4. This is the value of 3K here. This resistance is 3K, right? There are the two resistance here, 1K and 3K. So you can find out this V1, and V0 is plus V set and minus V set, and we know the characteristics of the hysteresis characteristics of bistable multivibrator. It is V0 versus Vi, and this point is the upper trigger point, this point is the lower trigger point, this point is plus V set, this point is minus V set, and plus V set minus V set is already given. It is plus 16 voltage, minus 16 voltage, and based on this expression you can find out this plus V set and minus V set. For plus V set the value is 16, and minus V set put the value minus 16. Here plus 16 minus 16, you find here 7 voltage and minus 1 voltage, and difference of these voltage, upper trigger voltage and lower trigger voltage, known as hysteresis width. So finally come to the 8 voltage. So let's consider second problem on bistable multivibrator. Now this circuit is very interesting here, because here we have just reverse the polarity. I mean here this is the negative, here the input signal is the circuit, the non-inverting type segment trigger, and non-inverting type segment trigger, that means you are applying the input, you are applying the input to the non-inverting terminal. When you just recall that circuit, here in this circuit you have given the input to the inverting terminal, you are giving the input to the inverting terminal. So this is the inverting type segment trigger. Now this way, so this is the non-inverting type segment trigger, because we are applying the input signal to the non-inverting terminal here. This is the non-inverting segment trigger, right? So likewise you can find out there are the two source voltage, same superposition theorem, there are two source voltage here, Vi and V0. You can find out this node voltage V1, same relationship you can find out. Now plus V set and minus V set already given to you. This is 10 voltage, and V0 is plus 10 and minus 10. So by this way you can find out their upper trigger voltage and the lower trigger voltage, and the difference of these is hysteresis width. Now you have to find out here the direction is very important, because at that time the transition is very simple, from plus V set to the minus V set to minus V set to plus V set. Here the polarity in non-inverting type segment trigger, this direction is in the anti-clockwise direction. While on the other hand, when we inverting type segment trigger, the was clockwise in the hysteresis. Because that was very simple, because the transition is from plus V set to minus V set only. This direction is clockwise direction only. So you can understand the here operation simple. This is a very simple operation. You can consider the minus V set and plus V set. Let V0 is minus 10 volt, mean minus V set. Then what is V1 here? 4 Vi minus 10 divided by 5. Right? Now if this Vd, if now there is transition from minus 10 to 10. When it will occur? Transition minus 10 to 10, when it will occur? It is occur when Vd is greater than 0. When Vd is greater than 0, what is Vd here? Vd, one terminal is already connected to ground only. What is Vd here? Vd is nothing but V1 only. So V1, when this is greater than 0, then you can find the inequality. Vi greater than 2.5 voltage. When Vi greater than 2.5 voltage, there is a transition from minus 10 to 10. Remember this. When Vi greater than 2.5 voltage, when Vi greater than 2.5 voltage, when Vi greater, this is the Vi greater than 2.5 voltage, there is a transition from minus 10 to 10. That's why direction is from downward to the upward, right? See, likewise, when consider the second case, when V naught is plus 10 voltage, V naught is plus 10, put in this relationship, VI is 4, VI plus 10 divided by 5, right? Now you have to transition, because plus 10 to the minus 10, when it will occur? When this VD is greater than 0. When VD greater than 0, mean V1 greater than 0. Sorry, it is less smaller. If VD is smaller than 0, then when V1 is less, it is smaller than 0, means 4V1 minus 10 divided by 5 is less than 0. You can find out VI is less than minus 2.5, right? So VI, you have to clearly understand this thing. Mean when the transition is occurring, mean you have to find out, mean there is always transition now, plus V set to minus V set, minus V set to plus V set, depending upon this difference input signal only. So don't confuse in this. There is a transition from now from plus V set to the minus V set when Vi is less than minus 2.5 voltage. When Vi is less than minus 2.5 voltage, when Vi is less than minus 2.5 voltage, there is a transition from this. So that's why this direction is in the anti-clockwise direction. Right. Now come to the stable multivibrator. As the term state, stable multivibrator, there is no stable states. No stable states mean both states are semi-stable. Mean if you have to attain, if you want to attain the semi-stable state, you required some circuit, you required some feedback. But what is interesting here, interesting in the stable multivibrator is that there is no external input. This is very interesting here. Without no external input, this circuit is generating a square wave generator, or you can say it is a free running oscillator. If you this actually this circuit is the non-inverting type, sorry, inverting type segment trigger. It is an inverting type segment trigger with additional to the this RC network, or you can say if an additional RC network connected in the segment trigger, then it is a stable multivibrator. You can remember in this way. If you close, if these are not there, then it is simply segment trigger only, non-inverting type. Mean here Vi only, here this is Vi, then it is the inverting type segment trigger only. Now if you want to make it as a stable multivibrator, just add on RC network only. Add on RC network only. This is RC network, that will be a segment trigger. Right. Now based on same concept, what is V1 here? This node voltage is the V1, and this is the VC. You see the voltage across this capacitor, and we know it is plus V set and minus V set. Here these are the two resistance, R1 and R2. This is the node voltage V1. Now what is the V1? V1 is the voltage across R1. So V1 is V0 into R1 divided by R1 plus R2. Now we are defining this resistance R1 divided by R1 plus R2 as a beta feedback factor. Right? To better understanding, we are representing as a beta. So what is V1 here? V1 is nothing but it is beta V0. And what is V0? V0 have two values, plus V set and minus V set. Right. Now what is the difference input? What is difference input? Now because every time you have to think in your mind that op-amp amplify the difference input signal only. You have to write in every question, you have to write what is VD. T nothing but V1 minus at this node, add input at this node, difference of input at positive node minus difference of input at this node, negative node. So what is VD? V1 minus VC. So VD is V1 minus VC. Now is it positive feedback circuit? Because it by seeing it is showing that it has both positive feedback and negative feedback, but I am seeing it is positive feedback. Now how can you test? Same concept you have to apply. Whatever the fact I have already defined you, same fact you have to apply. How you can apply the same concept? Same. If output voltage V0 increases, if output voltage V0 increases, if this output voltage V0 increases, then V1 will also increase. If V1 is increasing, means VD is also increasing. If VD means this difference is increasing, means output voltage is also increasing. So whatever the input you are, whatever the output voltage increasing, then it it will attain the high increase in output voltage. So it is a positive feedback only, right? Here, so that's why it is a positive feedback network, right? So this is the test for the positive feedback. Now this is capacitor here. Now the niche, what is the nature of the capacitor? Capacitor cannot charge instantaneously. The VC voltage cannot increase instantaneously, right? So that's why VD, that's why VD is increasing. You can also think that if V not increases, V1 is increasing. V1 is increasing, but what is there any effect on this VC? No, there is no effect on VC. Here the effect is very negligible. Why? Because the capacitor cannot increase instantaneously. That's why VD increasing mean finally in turn to the increase in the output voltage, right? So what output voltage may be of two type, mean output voltage may be either plus V set and minus V set. If output voltage is plus V set, then V1 is plus beta V set. If output voltage is minus V set, then it is minus beta V set. So these are the two points, upper trigger point or lower trigger point. Now in this like same Schmidt trigger, you are comparing this V1 with VC. V1 with VC, right? So what is VD here? VD is the difference of V1 minus VC. What is V1 here? V1 is this value, beta V naught. What is V naught here? Plus V set and minus V set. So you can write this V1 is plus beta V set, it is upper trigger point. So we can write VD is beta V set minus VC. Now you have to compare this VC and beta V set, right? So this is simple differentiation. This is simple differentiation. Now capacitor. Now in this way, in this circuit, you can now there are the two cases here, plus V set and minus V set. Now you are comparing this. Now here in this case, when V naught is plus V set, when V naught is plus V set, when V naught is plus V set. Now what is the effect on the capacitor? When V naught is plus V set, when V naught is plus V set, this capacitor will charge. This capacitor will charge through this resistance R, right? Because and when V naught is plus V set, this capacitor charges through this resistance R. So op-amp provides the charging current to the capacitor, right? Now capacitor, what is the nature of the capacitor? Capacitor charge exponentially, and capacitor charge discharge exponentially. And how much amount it will charge? I mean it will charge up to which voltage? This capacitor VC will charge up to this voltage only. Up to this voltage only. What is this voltage here? In plus beta V set condition, this voltage is beta V set. So we can in graphical way you can represent it. Output voltage is plus V set and minus V set, correct? When output is plus V set, when output is plus V set, right? When we are at this level, when output is plus V set, this is the output is plus V set. The capacitor is charging up to how much amount voltage? Plus beta V set only. This is the first case only. When output voltage is minus V set, then capacitor will discharge, and through which path? It will same path. It will discharge through the same path. Means this capacitor will discharge through this path only. So the charging constant RC and charging constant RC and discharging constant RC both are same. That's why it will generate a pulse of equal on equal of time, mean 50% duty cycle, you can say. So it is when output voltage is minus V set, it is discharging here. This is the nature of discharging. This is the nature of discharging here. It is this is charging here. This is discharge. Again same path. Charging and discharging. Charging. This is the wave generate. Then is the sphere wave, and what is the behavior of the capacitor? This is the behavior of the capacitor VC, right? This is the behavior of capacitor. Now what is interesting? Most interesting is to understand their time period. Mean how you can calculate the time period. Mean here by the graphical way you can clearly see that there are the time. Let us suppose this pulse we have generated here having the time period T naught. This pulse half period is T naught by 2. This half period is T naught by 2. At time T equal to T naught, at time T equal to T naught, what is VC here? Minus V set, right? When V naught is plus V set, it show the charging of capacitor. This is the charging of capacitor to the how much voltage? This voltage. Right. So at t equal to 0, what is Vc? It is minus V set. This is initial value. This is the initial condition at t equal to 0 negative. At t equal to 0 negative, it is minus V set, and at t equal to 0 positive, it is minus V set only. Why? Because the capacitor does not allow the sudden change of the voltage only. So Vc at 0 negative and 0 positive, it is minus beta V set. Right. Now what is final value here? In the finally it is V set only. Final voltage, what is V final? V final is plus V set only. Right. Now, as per the transient analysis, if you find out the voltage across the capacitor, you can easily find out the initial value minus final value multiply by e to the power minus t divided by time constant here. Here the timing constant for charging and discharging is RC only. Because capacitor is charging through this path and discharging through this path only. Here the path we have noted here, charging, discharging, RC only. So this is the initial value minus final value e to power minus t by RC, right? Plus final value. What is final value? Plus V set. Initial value minus beta V set. And what is final value? V set. So you can find out Vc is V set 1 minus 1 plus beta e to power minus t upon RC. So what at t equal to t naught by 2 means at this interval, what is the value of Vc? It's plus beta V set only. So put this value here at t equal to t naught by 2. What is Vc here? Plus beta V set. Here you can write at t equal to t naught, Vc is plus beta V set. Then you can find out the time period. This is the time period t equal to 2 RC ln 1 plus beta divided by 1 minus beta. What is beta? Beta is the feedback factor that is calculated from a resistance divider network, that is R1 divided by R1 plus R2. And what is frequency? If you have to find out the operating frequency of the pulse you have generated, then it is calculated by f naught equal to 1 divided by t naught, right? Now let's suppose there is one case here. The resistance we are taking here, because in a feedback network we have assumed the resistance R1 and R2, right? If these two resistance having the same value R, then you can find out beta will be half. So time period is 2 RC ln of 3. This is the way to calculate the time period of the pulse that is generated from the stable multivibrator, right? So now come to the monostable multivibrator. Now monostable multivibrator, with the meaning of the name, monostable means there is only one stable state, and second state is quasi-stable state. Quasi-stable state means how you can analog with the physical meaning. For example, suppose there is some heel and there is a ball here, right? At this ball on a heel, it can reside here. Means is it possible to retain this ball on a top of the hill? No, it will be either here or it will be either here only. So this is one state only. This is one state only. This state is the mean it can reside, mean it can stay here for only few period of time. So this state we represent as a quasi-stable state. In quasi-stable state, it does not mean that the output voltage is not plus V set or minus V set. You can treat any voltage as a quasi-stable state or the stable state. So for this time, I am considering V naught equal to plus V set as a stable state, and V naught equal to minus V set, it is a quasi-stable state. And if you can remember a quasi-stable state in your mind, that for a slight period of time, for a little period of time, there is some output, that is quasi-stable state only, right? And this stable state is mean output remain in this stable state until and unless there is no trigger is applied, right? Means your circuit having this state only, but if you apply external trigger, then it will switch from plus V set to minus V set, right? So in this circuit is very simple. Mean here what you are doing additionally, mean we are making flow of this connection. First we have studied the bistable multivibrator, now stable multivibrator, now monostable multivibrator. In stable multivibrator there is resistance and capacitance and the resistor network. Now what we are doing here, the important thing, there is a trigger generator and there is diode here. This is the one. These are the additional things we have done here. These are the additional things we have done here. If external input applied, then output remain in stable state. If you, when this trigger, you have to, because you want to other state na, so you have to apply some trigger. Here there is a trigger at this point, there is a trigger here. This is trigger generator, mean you have pulse input, you have some pulse input, and with the help of trigger generator you can generate a trigger, either positive spike or negative spike. Here I am generating the, with the help of trigger generator, I am generating a negative spikes. Mean you are generating this negative spikes, zero negative spike. With the help of this trigger generator, this negative spike I am generating, right? This negative spike will enable the input V1 to switch the output we know from plus V set to the minus V set. Likewise, other vibrator, there are two cases here. Now let us suppose there is a case when no trigger is applied. No trigger is applied means, as the name suggests, output remain stable state. What is stable state we have considered here? The stable state we have considered the V0 equal to plus V set. Can you find out the V1? Same relationship. V1 is nothing but voltage across the R1. V0 multiply by R1 divided by R1 plus R2. This now you are defining R1 divided by R1 plus R2 as a beta. So this is beta V set here. So V1 is this value only. Now this is the first case you are considering, right? Now what is the nature of the capacitor at this case? This capacitor will charge it through this resistance R. This capacitor will charge it through this resistance R, right? So VC will increase. But now what is interesting, now this capacitor will charge not to this voltage, like in case of a stable multivibrator, this capacitor charge to the plus beta V set, right? Now this capacitor will charge to this voltage, this mean voltage, the voltage of the diode. This is the design constraint here. Mean here the resistance R1 and R2 we are selecting such that beta V set, because it may charge to the beta V set also. But here we are, this is our designing constraint in the designing of this monostable multivibrator. This beta V set is greater than cut-in voltage. So capacitor will charge to the nearby voltage V gamma. So this capacitor will charge the cut-in voltage of the diode. So that means this voltage V1 is greater than Vc. Right. Now let us suppose you are applying a trigger. This is here input is the pulse, and based on this trigger generator you are getting this negative spikes. Right. It is very easy to generate the pulse, but it is not easy to generate the negative spike. Or to generate the negative spike, you are taking this is the circuit here, right? So now with the, when you are applying the negative spike, when negative spikes are present, the term is very important, negative spike. When a negative spike is present, when negative spike is present, now here at this point there is negative spike. I am drawing, there is negative spike. Due to negative spike, this voltage V1 will decrease. This voltage V1 will decrease. V1 will decrease. And what is the voltage here? What is Vc here? Vc is nothing but V gamma. Cut-in voltage here. So if this V1 decrease, if V1 is decreasing and it is less than, if V1 is decreasing and become less than V gamma, if V1 is less than V gamma, and what is the difference of, what is Vd here? Vd the difference of V1 minus V gamma only. Or V1, now V1 is less than V gamma. So what is Vd here? Vd is negative. If Vd is negative, Vd negative means output will switch. When output is, when no trigger, output is plus V set here. When you are applying the V trigger applying, so what is output here? Now at this moment, output instantaneously switches to the minus V set due to this trigger. Now I am repeating again, due to negative spike, this voltage V1 will decrease. If this voltage V1 decrease, mean positive terminal is decreasing. Positive terminal is decreasing mean Vd. Positive is decreasing. Vd is the positive minus negative. So Vd will also negative. If Vd is negative mean, since this is operation amplifier, if Vd is decreasing mean output will be minus V set. So output is minus V set mean, it means output is changes from stable state to the quasi stable state minus V set. Right. So I am representing same in graphical way. The output is either plus V set and minus V set. When output is, when no trigger applied, the output is plus V set only. This is plus V set. Right. And capacitor will discharge. In this, when output is minus V, now when V1 becomes minus V set, Now when V1 is minus, when V1 is minus V set, means V naught equal to minus V set only. Sorry, when V naught is minus V set only. What is VD here? VD the difference of positive, that is minus V set, and what is negative here? Negative means voltage applied at negative terminal. What is the voltage applied negative terminal? VC only or V gamma only. So minus beta V set minus VC. So output. So here the output capacitor start discharging. In this movement, capacitor start discharging. So in this case, you can, when output is minus V set, when output is minus V set, this capacitor will discharge. Capacitor start discharging in the direction of minus V set only. So capacitor start discharging in this direction. Capacitor start discharging. What is the nature of the capacitor? The voltage across the capacitor decrease exponentially up to how much voltage? Now this is very interesting. Charging is the V gamma, but discharging is not the V gamma. Discharging is this value minus beta V set. Why? Why this is happening? Because when capacitor start discharging, Vc is slightly less than minus beta V set. That's why output changes to the minus V set and capacitor start discharging. This is the nature of the capacitor. So capacitor start discharging to the minus. This line is the minus beta V set. This is the nature of the capacitor discharging. Right. So V set minus V set. If anyone is noting on your netbook now, then you can understand this. The V set minus V set, and this is the nature of the capacitor. So capacitor is discharging. So in this way, output voltage is a negative pulse. This is quasi-stable state. So this is the quasi-stable state. So now likewise the stable multivibrator, you can calculate the pulse duration also. You can calculate this pulse duration also. So how you can calculate this pulse duration? Same relationship. The voltage across the capacitor is initial value minus final value multiply by e to the power minus t divided by time constant plus final value. Right? At t equal to 0, from this graph, at t equal to 0, what is Vc, voltage across the capacitor? Vc is V gamma only. At that time, Vc is V gamma initially. For t greater than 0, capacitor start discharging. So Vc is minus V set plus V gamma plus V set e to the power minus t upon Rc. Right? So at t equal to 0, I am erasing this. Please remember this line. This is minus beta V set. You can remember in this mind, this is minus beta V set. At t equal to 0, what is Vc here? Minus beta V set. So put this value. Vc is minus beta V set minus V set V gamma plus V set minus t upon Rc. You are calculating at the moment of t naught only, means at this duration only. So t naught. So you can calculate the value of e to the power t naught divided by Rc. This is the expression here. Now taking the natural log on both sides, so you can find out this is the t naught divided by Rc. So adjusting the some parameters, so you can find t naught equal to Rc ln of V gamma V set into 1 minus gamma. Right? Now if V gamma is less than V set, if V gamma is less than V set, mean you can ignore the V gamma. So t equal to Rc ln of V set divided by V set into 1 minus beta. So V set will cancel out. So we are left with this t naught equal to Rc ln of 1 upon 1 minus beta. Here what is beta here? Beta is calculated from the feedback network. It is R1 divided by R1 plus R2, right? Now let us suppose there is a case when the resistance R1 and R2 we have opted having the same value of R. So what is Rc here? T naught here. So beta, what is beta here? Beta is half only. So you can find out T naught equal to Rc ln of 0.69 Rc. This is the pulse duration. So you positive pulse. Now here you have obtained the negative pulse here. Now if you want to find the positive pulse, now what you can do? Just reverse the polarity of the diode. Now diode is in downward direction. If you make the diode in the upward direction, so it will generate a pulse of positive pulse, right? So please note this line. Positive pulse output can be obtained by reversing the diode. Right. Now in this discussion, bistable multivibrator, astable multivibrator, monostable multivibrator, we have understand the how you can use the multi vibrator to generate a pulse, square wave, and
Hello?
negative pulse also. Now let's
Hello?
come to the
Dr. Gitna?
waveform generator.
Hello? Am I audible?
Yes, ma'am. Yes, ma'am.
Dr. Gitna, let us take a 5 minutes break. It's already been 1 hour, so you also please take some water or something so that after 5 minutes, 12:10, let us be back at 12:10. Is it fine with the audience? I write the chat box. We are back at 12:10. Yes, please, Dr. Girdhar, let's take a break of 5 to 7 minutes.
Yes, ma'am. Yes. Okay.
Okay, so we will be back at 12:10. Yes, so Dr. Girdhar, can we start? Am I audible?
Yes, 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 ma'am. We can start.
Okay, 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 please continue.
Okay, till now we have discussed the multivibrator, and after that we have generated how they can be useful in designing the square wave and the pulse output with the help of multivibrator. Now let's continue our discussion with the other waveform generator also. For example, ramp generator or triangular waveform generator, right? So this is the triangular waveform generator. I have let's consider this circuit, and in the circuit, if you see this is a schematic trigger. The circuit is the non-inverting type schematic trigger. I mean, why it is non-inverting type? Because this in because and we, this is minus, and actually this is minus, and this is plus. Please note this line. This is minus and this is plus. It is non-inverting type schematic trigger. Mean here the input signal Vs, this Vx you are applying as a input to the positive signal only. That's why it is a non-inverting type trigger, or you can see it is the regenerative comparator. Right here the inverting terminal is connected to the ground. This circuit is the Smith trigger that will generate a square wave, that will generate a square pulse, right? That will generate a sorry, that will generate a that will generate a square wave, that will generate the square wave. This is the square wave that will generate a square wave. Now you have to generate the triangular wave. Now what is the concept here? The concept is that if you integrate the square waveform, then it will form a ramp signal. Mean you are integrating a square signal, it will generate a ramp signal, right? So and the collection of the ramp signal, it will form a triangular wave. So you have to understand this thing. So, and so add this node V01 is the square wave output, and this circuit is the integrator. The integration of V node, it will give the V node as a triangular wave, right? So now what is Vx? So for this you can understand that what is Vx here. Vx is the source voltage across the R1 only. So you can write, there are the two voltage here, V01, this is the one voltage V01, this is the another voltage V no, and you have to find out this voltage Vx, right? Now what is the node voltage Vx here? Actually the node voltage is the voltage across a node. No, the node voltage is the voltage, mean the potential difference. Actually the potential difference in between two nodes. And you are taking the potential difference at a node, mean potential with respect to ground. When you are taking the potential at Vx, mean second term should be ground only. So that's why in superposition theorem you will follow the one source voltage connected to the ground only. So there are the two source voltages, V01 and V no, and you have to find out this Vx. Now you have to find out this Vx, right? How you can find out Vx? Let us suppose you are considering this V0 only and this V01 connected to the ground. Then if what should be the Vx here? Vx is the V01 R1 divided by R1 plus R2. Now at this moment the voltage is it is R2, because you are putting V01 as a 0. It is 0, right? It is 0. You are considering this V0 only. So what is Vx here? V0 R2 divided by R1 plus R2. This is one voltage. In second case, let us considering the V0 is connected to the ground, and you are taking the source voltage V0 only, and you have to calculate Vx. What is Vx here? V01 multiplied by this resistance R1 divided by R1 plus R2. Now you are adding these value. The value totally give this voltage Vx, right? Now in Schmitt trigger it is basically comparator circuit, right? Because you have already compared the input signal with the voltage that we define as upper trigger voltage and lower trigger voltage. Same concept is also applicable here. Now in this case, what is Vd here? What is Vd mean? Difference in input signal. Difference in input signal, it is Vx, it is ground. So when Vx is greater than 0, When Vx is greater than 0, V naught is plus V set. When Vx is less than 0, V naught is minus V set. Same concept. This is the operation amplifier A1 that generated square wave on input. Right. So V01 is the square wave output. Now you have to integrate. What is the relationship of integrator to calculate the output expression? We know this relationship. V naught is minus RC integration of V01. Here V01 act as input to this amplifier A2. So minus 1 upon RC integration of 0 to V01 dt, right? So now what is V01? It is either plus V set or minus V set. When V01 is plus V set means square pulse means positive pulse, plus V set means positive pulse here. When it is plus V set integration of this signal, it will generate a ramp signal. It is plus, actually it is plus minus, it will generate the negative ramp. When it is minus V set, minus plus, so it will generate the positive ramp. So you can understand in this waveform also. Output is either plus V set or minus V set. When output is plus V set, then it generates a negative ramp. It generates the negative ramp. So negative ramp signal you can draw this. This is the negative ramp signal. When output is minus V set, it generates a positive ramp. Again negative ramp, positive ramp. In this way you are generating a triangular waveform, right? And as per the design constraints of triangular waveform, this triangular waveform, it will generate a ramp signal or triangular signal having peak to peak value minus Vm to plus Vm, mean it is total value is 2 Vm only. Peak to peak voltage swing is 2 Vm only, right? And this value Vm is defined with this Vm you cannot choose by your own, because you have to take it as a granted with the help of designing parameter, because these resistance R1 and R2 you have to choose practically. What is the value of Vm and minus Vm? This is you have to remember the relationship. Vm is nothing but it is R1 divided by R2 in V set. Right, this is the value of Vm. Then you can draw this triangular waveform. Otherwise, you cannot draw the triangular waveform. If you are generating a triangular waveform or any other waveform, the two factors are very important. One is gain and another is frequency. Mean one is peak voltage and other is frequency. Mean time period that is required. So peak voltage is calculated with the help of this relationship. Now come to the time period. Now what is the time period here? For calculating the time period, we have already told you have to consider only the expression only. Now in this case, you are having a integrator. What is the expression of the integrator here? V naught is nothing but it is integration of output signal V naught t, defined with the help of time circuit component RC, minus 1 upon RC integration of V01 dt. Right. Now from T0, this is T equal to 0. Now let's suppose this is our pulse. For better understanding, now you are considering this pulse interval, negative, positive. The total pulse we have considered, this is the T naught time period, right? Now, in this at this moment, what is the change in the peak output voltage? Minus Vm to Pm, it is 2 Vm only. So minus RC integration of G to T2. For A2, it is minus Vm to plus Vm. So it is 2 Vm integration 0 to T by 2. What is V01 here? V01, it will be output voltage. So it is output voltage V01, it is output voltage, whose output voltage it is? It is the output voltage of Schmitt trigger. So it is either plus V set or minus V set. In this case, when you are taking the minus V set, so it is minus V set only. So minus plus, so 2 R1 divided by R2 into V01, V set divided by RC into T naught by 2. So you can find out this pulse period T naught equal to 4 RC R1 by R2. Now you have to calculate the operating frequency of this triangular waveform generator. So you can calculate F naught equal to 1 upon T naught. Now let's suppose one case is when both resistance having the same value R1 R2 equal to R, then you can find out the time period is nothing but it is 4 RC. Right. This is the now we have completed the waveform generation. It's a non-sinusoidal waveform generation. Right. Now let's come to the timers. And now the timer is a triple fab timer. As the name suggests, it is a timer IC. Triple fab timer, it is timer IC. It is 8-pin IC. IC means there are the many circuit components here. When you see the internal schematic of this timer IC, you would think externally there are 8 pins here. Externally in a triple fab timer, there are the 8 pins, right? I can zoom it. There are the 8 pin in this. There are the 8 pin here, right? In 8 pin, and when you see the internal body of this timer IC, you will find that there are the two comparator. Upper comparator, this is upper comparator, this is lower comparator, one flip flop, and there are the two BJT here, two BJT bipolar junction transistor. One is in the NPN configuration, another in the PNP configuration, and there is a power amplifier. Here the power amplifier is working as a NOT gate, as an inverter, right? So each pin have their own function. Each pin has their own function. Now, what is the meaning of this triple FAM? The 5 means there are the 3 5 kilo ohm resistor you are connecting here. 5 kilo ohm resistor, second 5 kilo ohm resistor, and 3 5 kilo ohm resistor. These are connected in the form of series, and these 3 resistance it form a network or a voltage divider network, right? Mean these form a voltage divider network, upper comparator and lower comparator. Comparator, meaning of the comparator is very simple. It compare the input signal with the other reference input signal and give the output. This is the meaning here. So for example, this is the upper comparator. The internal schematic you have to understand very clearly. For example, this is upper comparator, and this is positive terminal, this is negative terminal. Whenever the input voltage on positive terminal is greater than input voltage in negative terminal, then comparator generate the logic 1 output. Right? This is the behavior of this comparator. Or in another way, this, if non-inverting voltage, if this voltage is smaller than this voltage, then it will give a 0 output, right? So this is the way how you can understand the basic functioning of this comparator, right? These 3 resistance R1, R2 and R3 are in series. Now why these are in series? Because they you know the operation of the operational amplifier. In case of the operational amplifier, there is no current is flowing inside the op-amp because input resistance is infinite. So the all 3 resistance are in series. If all 3 resistance are in series, here I am writing here, this is the resistance R1, R2 and R3. This is the resistance R1, this is the resistance R2, and this is the resistance R3, and total supply voltage we are taking as a VCC, right? And it is connected to ground. And this is the it is going to the lower comparator, and this is going to the upper comparator. Now can you find out voltage here? Voltage at this node, can you find out voltage at this node? And if you are assuming these resistance are of equal value, these resistance R1, R2 and R3, these are equal value, 5 kilo ohm only, then can you find out this value? This node, voltage at this node is simple, VCC by 3. Voltage at this node is, voltage at this node means voltage across R2 and R3, means 2 resistance here. So it is 2 VCC by 3. So these are the voltage, VCC by 3 and 2 VCC by 3, right? So this is the way you can understand and the behavior of this. Now come to application of this timer FC. How it is applicable in monopole and stable multivibrator. Right. So now, and this is the operation of SR flip flop. Everyone know the operation of the SR flip flop. S is the set input, R the reset input. This is the next state, and depending upon S and R, the output is decided. This output goes to the This output goes to the power amplifier. Power amplifier here working as a NOT gate. Now, what is the use of power amplifier? Actually, power amplifier used in the internal circuit of the triple FAM IC because it can supply the larger output power to the load. Here, this is the use of the power amplifier in triple FAM because so that it can supply the large output power to the load. Right here, why what transistor we are taking here? What is here? There is 2 transistor here. Why we are taking here the transistor Q1? It is used to reset the output. Right. This transistor Q2, this is used as a discharging transistor because it provides the discharge part to the capacitor. Because it provides a discharging part to the externally connected capacitor. So these are the pins here. You can remember this is the pin number 1, pin number 2 trigger input, pin number 7 charge, pin number 5 control, pin number 6 threshold, pin number 8 power supply voltage, pin number 4 reset, pin number 3 is the pin at across which you are taking the output, right? And here the input is QR only, not Q. Now we come to the 555 timer IC, the application of 555 timer IC. These are in monostable multivibrator and the unstable multivibrator. So let's start from the monostable multivibrator. Monostable multivibrator we have already discussed. It has only one stable state. Now what you have to attend another state, that is quasi-stable state. Regarding this, you have to require a trigger. Monostable. What is the use of monostable multivibrator or 555 timer IC? Because it can be used as a delay circuit. It can be used as a delay circuit because sometimes we require a delay, time delay in the digital circuit. Like for example, in some time you find that you have to introduce the delay. Delay can be introduced with the help of this 555 timer IC, or when you have to introduce some clock skew, or when propagation delay of any digital circuit, you can incorporate the effect of this multivibrator in the designing of digital circuit, so that after that you can analyze their effect, how the clock skew and the other delay is helpful in deciding the setup time, hold time, propagation delay, and the contamination delay. So this is very powerful IC. Actually, this 555 timer IC, this is very powerful IC because it can also be used as a pulse stretcher. Because by this IC you can stretch the pulse duration also. Mean you can vary the duty cycle also. So this is the 8-pin IC we have already spoken, and these are some connections. You have to remember these connections, right? For example, there is externally connected resistor, externally connected capacitor, and these pins, and this is the capacitor of 0.01 microfarad, right? Now we are understanding the monostable multivibrator. Monostable multivibrator means only one stable state. You have to choose wisely what states you are choosing here. Now for my convenience, I am choosing V naught equal to 0 as a stable state, right? Now V naught as a stable state, and what is the quasi stable state? It reverse. So quasi stable state is V naught equal to 1 or VCC. It is the quasi stable state. In this state, your output will remain until in the state output will remain whenever the trigger is activated, right? So whenever trigger is not applied, then output remain in the stable state. What is the stable state you have considered here? V naught equal to 0. This is the stable state here. V naught equal to 0, right? So now please try to understand this circuit. This is the circuit I have taken. By this circuit, you can understand the basic functioning of this monostable multivibrator, right? Whenever there is no trigger, output, this triple IC timer IC is in a stable state. Mean output voltage be 0, output voltage in stable state. But we have assumed, for my case, I have assumed this is 0, right? If it is 0, what is this power amplifier? It is working as not gate. If it is 0, mean this is 1 here. QR is 1. QR is 1, or this connection, this QR is 1, mean this one is going to this transistor only, this Q2 only. If QR is 1, mean as a base terminal, you are applying a logic 1, mean this transistor will be activated, this transistor. So this transistor is on, so now capacitor have path. So capacitor will discharge fully through this Q. Capacitor will charge fully through this. Now in this case, capacitor will discharge fully through this Q2. So what is the voltage we see here? The voltage across this is 0. So we see 0. This is the case. And whenever output voltage is in stable state, when no trigger apply, we see 0. Mean initially no trigger apply, we see 0. Please remember this line. Now you are applying a trigger. And as we have already told, trigger we are assuming as a negative spike. Now you are applying a trigger only. Trigger is the negative spike. Whenever the negative spike is applied, now here where you have to apply the trigger, here whenever trigger is negative spike, this is the second number pin. At the second number pin, you have to apply the negative spike. Whenever the negative spike, this is the trigger input. Add this is the second number pin. At this point, you are applying a negative spec. This is negative spec. Whenever you are, it is zero negative spec. It is zero negative. Whenever the spike is applied, the voltage at trigger input, it is zero. So lower comparator, this is upper comparator, this is upper comparator, and this is lower comparator. Whenever this input, second input, negative input is zero, first input is VCC by 3. Now what is the difference here? Difference is VCC by 3 minus 0, mean a difference amplifier. So op-amp, it output will be 1. So output will be 1. Why? Because it is positive now. VCC by 3. So it is 1. So this is flip-flop. If set input is 1, so output will act as a set input to the 1. If S is 1, S1 means Q is set, Q is 1. What is QR? QR is 0. If Q is 1, QR 0. What is the output here? Output is V0 is Q1, QR is 0. This is QR is 0. Q1 means set kiya, Q is 1, QR 0. What is output here? Output is, now output is 1 here. So V0 changes to the quasi-stable state because we have already considered the stable state is 0, quasi-stable state is 1, right? So this is the operation here when now output is 1. Now let's do the reverse engineering. Now output is 1. I am erasing this, and output is 1 here. This is the output is 1. Now you have output is 1 here. If this output is 1, output 1 means, since it is not gate here, output 1 means this is input should be 0. Input should be 0. If this input is 0 means this transistor will be off. This transistor will be off. This transistor Q2 is off. So discharging path that is applicable when no trigger is applied. So discharging path is disconnected. Here capacitor cannot discharge. Here capacitor cannot discharge. Then what capacitor will do? Capacitor will start charging through the resistance. So capacitor will start charging through this resistance. Please note this line, when V0 is 1. When V0 is 1, capacitor start charging. And what is the nature of the capacitor charging? Capacitor start charging exponentially. It starts charging or increasing exponentially. But how much amount? But how much amount? This terminal is connected to this node only, and this node having the voltage 2 VCC by 3. Same operation. So capacitor start charging or increasing exponentially up to 2 VCC by 3. Right. So if VC, this voltage, this potential is positive terminal is VC, this is 2 VCC by 3. If VC is greater than 2 VCC by 3, upper comparator generate a logic 1. So if it generates a logic 1 mean R is 1 mean reset. It will reset the flip-flop. So Q is 0, QR is 1. If QR is 1, so V0 will become to the 0. Hence output return back to the stable state. This is the operation of the triple FF timer as a monostable multivibrator, right? So based on this operation, I am drawing this waveform. This is the output voltage, and when V0 is 1, capacitor is start charging exponentially, and after that start charging. If VC greater than VCC 2 VCC by 3, upper comparator will 1, which act as reset the flip flop. Then V0 return back to the 0. So this is the operation waveform. Here how much amount capacitor charging? Capacitor charging to the 2 VCC by 3. I have already told it is 2 VCC by 3. So whatever the operation I have already told, I have represented in the graphical way in this. Right, this is the way. This curve is for capacitor charging and discharging, discharge charging, and capacitor discharging through the transistor Q2 only. Right. Now what is the voltage across the capacitor? The voltage across the capacitor is nothing but it is VCC into 1 minus. We are talking about the charging only. VC into 1 minus T upon RC. So at T equal to 0, it has the VC 2 VCC by 3. So you can put here 2 VCC by 3 V1 upon RC and find out this ampere T naught is RC ln of 3. So what is T naught here? T naught is 1.1 RC. When you calculate this with the help of scientific calculator, then you find a pulse duration having the pulse width 1.1 RC. Right. So pulse duration with the relationship you can comment that the pulse duration can be varied by changing the value of R and C. Right. So what is interesting here? Interesting is that triple 5 timer as a monostable multivibrator can be used as a ramp generator also. How? How you can generate a ramp generator? When this, when they, here the charging is, here charging is through this resistance only. If this resistance is replaced with the help of current, constant current source, when you are placing this resistance with a constant current source, then charging current to the capacitor, when the charging current to the capacitor is constant, then capacitor voltage increases linearly with time. So hence Vc will be a ramp signal. Hence Vc will be a ramp signal only. Because please note this relationship here. Vc is here Vc is 1 by C integration of I into dt. I into dt. I equal to C dVc by dt, right? I equal to C dVc by dt, mean current flowing across the capacitor represented by C dVc by dt, right? Now you can calculate the Vc here. Vc is 1 upon C integration of I dt. Now I is the constant current source here. Constant current source. So what is the voltage across the capacitor? Vc is 1 IC upon C dt. So it is a perfect ramp signal. So capacitor charging provide a perfect ramp signal, and there is a discharging. So like we discharging is again same perfect ramp signal, again same perfect ramp signal. So in this way you can generate a ramp generator also. So in this way triple five timer it work as a ramp generator also. Now at t equal to t naught, this is the duration here. At t equal to t naught, what is the voltage across the capacitor? Voltage across the capacitor is 2 by 3 VCC. 2 by 3 VCC. So you can find out the pulse duration also. Pulse duration of the ramp signal. This is the duration C divided by I 2 VCC by 3. Right. Now come to the use of triple five timer as a astable multivibrator. We know astable multivibrator means no stable state. Both are quasi-stable states. Right. Output have two quasi-stable states only, either logic 1, logic 0. It is also known as square wave generator or a free running oscillator also. Right, this is the internal schematic of triple five timer IC. Now, but you have to do the some external connection, and for the use of triple five timer as a stable multivibrator. In this case, you have to note that there is two resistance here. There are two externally connected resistance, RA and RB, right? And there is one more capacitance C. Now same thing are same, and these are the resistance network, resistance divider network, same potential VCC by 3, 2 VCC by 3, right? Same operation you have to understand. Now let us suppose stable multivibrator. Now let us suppose output has two quasi-stable states, either logic 1 or logic 0. Now first case we are considering as a V naught is 1. V naught is 1 here. Now let us consider V naught is 1 here. Mean output voltage is 1. Output voltage is 1. Output voltage is 1 mean this Q bar should be 0. Why? Because it is inverter. If it is 0, then it will be 1 na. So it is 0. If it is 0, this transistor Q2, so this transistor Q2 will be off. So this transistor Q2 is off, mean capacitor will not discharge. Capacitor cannot discharge. Then what capacitor will do? Capacitor will not stay idle. What it will do? It will charge through resistance RA and RB. So what is charging time constant here? So charging time constant is RA plus RB into C. Now how much amount of the voltage it will charge? So it will charge or it increase exponentially up to which voltage? Now you have, for this you have to see the connection here. Mean this VC is connected to the pin number 2 and pin number this one. So this is the potential this potential VC, and this for this upper comparator only. Upper comparator, this voltage is VC, and this voltage is VC. This and second voltage is 2 VCC by 3. So capacitor will charge up to which voltage? Up to 2 VCC, 2 by 3 VCC. So if this voltage VC is greater than 2 by 3 VCC, upper comparator give the logic 1 output. If it is logic 1 output, means it reset. Reset is activated. So it will flip-flop. So flip-flop will be in reset in input to the flip-flop. So Q is 0. Q is 0 means Q bar is 1. If Q bar is 1 means output is 0. Output is 0. In the output bar 1, you have the transition. So 1 to 0 this is occur in the output. Now you can understand in another way also. Let us suppose, if it is not clear, let us suppose second case. If V naught is 0. If V naught is 0, I am raising all thing here. If V naught is 0 here, if V naught is 0, if V naught is 0, if V naught is 0 mean, if this V naught is 0, since it is a not gate, inverter gate, and if this V naught is 0 mean this QR is should be 1. If this QR is 1 mean this transistor Q2 will be on, because you are applying a logic 1 at a base terminal, so this transistor will be on. If this transistor is on, so now this capacitor will discharge through which path? So this capacitor will discharge through this path RB, and this is the path to discharging RB only, not RA. This is the path here. Capacitor will discharge through this path only. Discharge. So capacitor will discharge only. Now what is the discharging constant here? Discharging constant is RV multiplied by C only. There is only one resistor RV. Now how much amount it will discharge? Mean how much amount this VC will decrease. So regarding this, you have to see the inputs. Here this is the VC, and this is the VC here, and what is the another input here? It is VCC by 3. So it will decrease. So voltage across the capacitor, it will decrease exponentially up to VCC by 3, right? If this VC is decreasing, right? If this VC is less than, if this VC mean negative is less than VCC by 3, right? Mean it is 1, logic 1. So it is logic 1 mean S equal to 1 mean it will set the flip flop. So Q will be 1. Q will be 1 mean QR will be 0. QR is 0 mean not gate. Since it is not gate, we are using power amplifier as a not gate. So output will be 1. So now your transition, now there is a transition from 0 to 1. So now there is 0 to 1 transition occur in the output. So in this way, output keep toggling in between logic 1 and logic 0. Thereby there is a logic 1, there is 1, 0, there is 1, there is 0, 1, there is 0, 1. In this way you are achieving a square wave output. In this way you are achieving there is a square wave output. Right. Now in this case, what is interesting the charging time. Here charging time is RA plus RB into C. The discharging time is RB into C. If the charging time is greater than discharging time, that's why output has duty cycle greater than 50. Mean on time period will be greater. On time period, if you see it clearly the figure, on time period is greater. On time period is greater than, this is on time period, it is greater than off time period. This is the nature of the capacitor charging. Capacitor charge up to 2 VCC by 3, discharge to VCC by 3. Based on the operation, I have written only the graphical representation only. Right. Now you can calculate their on time period. Mean on time mean charging constant RA plus RB into C 0.69, same likewise the monostable multivibrator. And low time there is only discharging only 0.69 RB plus RC only. Total time period is on time plus off time, mean T high plus T low, 0.69 RA plus 2 RB into C. And you why this is, what is frequency here? Frequency is 1 upon T naught. You can find out this is the frequency here. What is duty cycle? On period divided by total period. On period divided by total period. This is the on period T high divided by total period. This is the total period. So in this way you can calculate RA plus RB divided by RA plus 2RB. These relationships are very helpful in solving the problem, like a stable multivibrator using 2.5 timer is given to you, and now you have to calculate the frequency. Or you can say there is monostable multivibrator circuit is given to you using the 2.5 timer IC. Now then you have to calculate the total time period, or you can calculate the duty cycle. By this way you can do you can do the analysis, and you can represent a pulse and with their time period and with the duty cycle, right? Now in this way we have studied the monostable multivibrator and stable multivibrator using the 555 timer IC with the to generate the pulse output, right? Can we use a stable multivibrator as a voltage control oscillator? Yes, we can use the stable multivibrator as a voltage control oscillator. If a controlled input VT is applied at a pin number 5, mean you have to do some specification here. If you apply the at pin number 5, if you give the here capacitor is given, if you apply a VT here, then you can generate the sinusoidal wave. You can also generate a sinusoidal. So change in the VT, change in this potential will generate the change the frequency also. Mean ultimately when we say sinusoidal wave mean they have some frequency. Mean there are some tones here. Mean some frequency term here. So when you are changing the potential of this voltage signal, then you can vary the frequency. That's why this 555 timer IC that can be used as a voltage to frequency converter also. Mean you are varying the input signal voltage at pin number 5, you are getting a sinusoidal signal having a different frequency. That's why it is named as voltage to frequency converter also. We can use a stable multivibrator as a voltage control oscillator, volt frequency converter by some specific, by some dedicated specification, right? So now come to the problems. I have discussed some problem here. This is the 555 timer I have given, and you have to it is given with the a stable multivibrator using 555 timer, right? Now you have to calculate the frequency, and now you have to calculate the frequency. How you can calculate the frequency here? Now what should be the approach here? How you can calculate the frequency here? Mean this is the 555 timer IC using a stable multivibrator. How you can calculate? For this you have to understand the internal schematic here, right? Internal schematic have two comparator, upper comparator, lower comparator, and there is BJT also. Some portion, half portion that is required I have noted only, right? That is required only. Now what is the specification given in the problem here? I have seen a specification done in the internal schematic also. Mean there is a current source, or I have already told in case of the stable multivibrator having the resistance, if this resistance is replaced with a constant current source, then a ramp is formed. That's why this circuit is sawtooth waveform generator, sawtooth waveform, or a triangular waveform, right? Sawtooth waveform generator, right? So but now you can understand the operation. This is the transistor Q2 here. When this transistor is off, and when this transistor is off, capacitor charges through the, when this transistor is off, then capacitor will charge through this constant current source. This capacitor will charge through the constant current source. How much amount it will charge? It will charge up to 2 VCC by 3. It has, we have already described, it is 2 VCC by 3. What is VCC given? VC is given to the 5. So 2 multiplied by 5 divided by 3. So it will charge up to 10 by 3. So it will charge up to 10 by 3 voltage. Now when this transistor is on, then capacitor will discharge. How much amount will discharge? How much amount up to will discharge? It will discharge up to the VCC by 3. It will discharge up to this is the potential here, VCC by 3. What is VCC here? VCC 5 by 3. So this is the waveform I have presented, 2 VCC by 3. This is VCC by 3. Now in this way you can calculate now this is the waveform generated. Now you have to calculate the pulse waveform also. Or now we know the charge conversion principle. Now this is the I C dV equal to I into T, right? Here I is the constant current source we have given, T the time period we have assumed. For this sawtooth waveform it is T naught. Now C into del V the swing in voltage swing from VCC by 3 to the 2 VCC by 3. So it is 10 by 3 minus 5 by 3. Voltage swing we have calculated. Now in this way you can calculate the pulse duration, and by this way you can also calculate the frequency. In this circuit we have to calculate the frequency of the oscillation. That's why we have calculated first time period. After that we have calculated the frequency. Right. Now come to the second problem here. You have given a stable multivibrator using 555 timer IC, and since it is a stable multivibrator means circuit is oscillating steadily, mean indefinitely. So what is the voltage across the capacitor? You have to calculate here. Voltage, what is the range of the calculator? But we have already defined in lower comparator, we compare with the VC is compared with VCC by 3, and in the upper comparator it is compared with 2 VCC by 3. Right. So VC is compared with VC is compared with the 3 voltage here. In lower comparator, this VC, this is the voltage across the capacitor. This VC is compared with the voltage. When you see the internal schematic, this is lower comparator, this is upper comparator. This VC is compared with this voltage. VC is 3 voltage. So it will discharge up to 3 voltage only. In upper comparator, it is 2 VCC by 3. 2 VCC by 3. What is VCC? 9. 9 by 3, 3. 3 multiplied by 2, 6. So this potential is 6 only. So it will be charged up to 6 voltage. So what is the range of the capacitor only? 3 to 6 voltage only. 3 to 6 voltage only. In case lower voltage, what is the VCC by 3? What is VCC? 9 divided by 3. So it is 3 voltage. So it will discharge up to 3 voltage, charge up to 6 voltage. So range of the capacitor is 3 to 6 voltage only. Now let us suppose I have to ask some additional thing. That means what is the current? What is the current it is absorbing from the power supply here? So current it is, you can calculate here from 9 minus this potential is 6 divided by 13k, it is 0.1 milliampere. So you can find out the VC also. What is the potential across this node? The potential at this node is nothing but it is V1. This is the V1 minus this current, mean this potential, V1 minus this potential. What is the potential at 10k ampere? 10k multiplied by I, because all resistance are in series, 30 kilo ohm, 10 kilo ohm and 12 kilo ohm. Now you have to understand these are not the internal resistance, because internal resistance are 5k, 5k, 5k only. These are externally connected resistance, RA, RV and RT, right? So what is the VC here? VC is nothing but node potential V1 minus the potential across 10 kilo ohm. You can find out VC 5 volt and you can also find out this current I, right? So now in this talk I have discussed the use of multivibrator. Mean bistable multivibrator, there are 2 stable states only that is useful for memory storage, switching, and the most beautiful application in the latch and flip-flop here. In astable multivibrator, there is no stable state. There is free-running oscillator only that continuously switch in between 2 states that form a square wave, right? In monostable, it is also known as single shock that is useful for pulse generation and timing application. And one is stable state and another is one quasi-stable state, right? In non-linear waveform circuit, I have represented the triangular waveform generator and ramp generator and other applications also. And now what are the other circuits here? Non-linear waveform circuit. There are some circuits also, clipper, clamper. These are also non-linear waveforming circuit. I mean, they, depending upon the requirement of the customer, they can shape the waveform. They can shape the waveform. Clipper, positive clipper, negative clipper, clamper. They can shift the DC level also. These are also type of the non-linear waveform circuit. Because since our discussion was based on the op-amp only, that's why I have considered only the square wave, triangular waveform also. And after that we have discussed the timer IC, triple five timer IC, and its internal schematic of triple five timer IC, and how externally the distance are connected, how there is the charging and discharging path is provided in triple five timer IC, and how charging and discharging time period is helpful in calculation of the pulse duration. And depending upon the pulse duration, by varying the pulse duration, you can also make a pulse width modulator also. It is also useful in the pulse width modulation and oscillator application also. Here 2 applications we have discussed, monostable multivibrator and astable multivibrator is in the triple five timer. Now the book recommended from my side is Donald Newman, Electronic Circuit Analysis, and the second book for the problem solving you can do the Sadra Smith Microelectronic Circuit. Now there is time here, so we can also do some virtual lab. You can also do some experiments on the virtual lab also. Hello?
Yeah, please carry on.
So in virtual lab, there is one browser, or you can say there is one software that is developed by the renowned professor of IIT Roorkee. They have developed this virtual lab, and in this you can do any experiment. They have designing this lab or virtual lab in a very nice way, so that anyone having very little knowledge of electronic circuit, they can also do their experiment also, right? This is the theory they have provided here, right? Now we have come to the simulation part. Now this is the procedure here. In procedure, they have also given the connections. Mean you have to connect how you can make stable multivibrator using triple five, how you can make monostable multivibrator using triple five. This is the procedure they have given. I am skipping this and come to the simulation portion only. Right. Now let us start from the monostable multivibrator. Right. This is the circuit they have given. Triple five timer and CRO they have given, and this is the oscilloscope. Now they have given now if you are not having any knowledge here, right? If you remember any connection should be connected to. Now let us I do now I am doing intensely mistake, right? For example, I am connecting 1 2 3 and 2 to 4, like 7 to 6 and 8 to a this one is connected to 5. Now let's check the connection. You can check this connection. Please go through the instruction once. They are showing one pop-up message. Go to the instruction. Now in this you have given an instruction here. Mean you can use the triple five timer. They have provided their connection. You have to connect 1 to 3, 2 to 4, and 5 to 7, 6 to 8. Right. This is the connection you have to make. 1 to 3, 2 to 4, 7 to 5, 8 to 6. 1 to 1. You can also remember this as 1 to 3. You can remember this 1 to 3, 1 to 3, 2 to 4, 7 to 5, and 8 to 6. Now in this way you have to make the connection. Now we can 1 to 3 we are okay with, 2 to 4 we are okay with, 7 to 5 we are not okay. 7 to 5 you have to drag this 7 to 5.
Maybe you can delete all connections one time.
Okay, yes. 7 to 5, this is 7 to 5 we are connecting this, and now 8 to 6 we are connecting this. Now we can check the connection here. The connection are okay, right connection. Now you can start your experiment here. Now you have to, just like a PCB connection and breadboard connection, now you have to get the power supply. Now if you do the power, now you want to plot without power supply, I mean you can also do by your hand also plot. Please turn on the switch. It is saying that please turn. So I can power on. Now you have to choose. Here there is only here we are making the monostable multivibrator using triple five. There is only one resistance, only RA only. So you have to choose. You have to, because you have to plot the curve, na. So you can change the value of resistance. Mean here the tunable. Here resistance is made tunable. Mean you can varying the range. Here the resistance value is 0. The maximum you can go to the 70k. Mean they have. This is also the part of their design constant. Mean what's the maximum limit, maximum rating of this resistance, and what is the maximum rating. So maximum rating of this resistance is 17, and capacitance value that it is fixed at 0.1 microfarad. Right. So in this way you can plot. Suppose you have to now we have taken the value, this value here. This is the one value plot. We are going plot. Now this is now you can, I have taken three values now, 17, 10, 13. So in this way capacitance value is fixed at 0.1 microfarad only. Now based on the value of the resistance, or you can say based on the value of charging constant, because charging constant, discharging constant vary, so pulse is also changing here. This is the trigger voltage here, and this is the voltage across the capacitor. Because we have already spoken, in case of the monostable multivibrator, there is a charging and discharging here. So what is the output voltage? This output is in the form of the pulse. Now you can make you have to vary this pulse duration. You can, for varying this pulse duration, you can changing the value of the resistance only. This is the way you can make triple five timer as a monostable multivibrator. In the same way, you can design a stable multivibrator also. In case of the stable multivibrator, instruction they have written, There are the some
So,
instruction.
Dr. Girdhar,
Yes, ma'am.
thank you so much. I think it is 1 o'clock and they are actually waiting for the lunch.
Okay, ma'am.
So,
Okay.
if you permit, we can conclude the session.
Yes, ma'am. Last conclusion. So by this way, you can use the triple fab timer IC as a monostable and stable multivibrator also, and you can also do these experiment on there is some tool like Tina Texas Instrument. It is also very useful tool, and uh, and LT Space. It is applicable everywhere. So if any query, and you can ask me.
Yes, please, if there is any query, please ask. Otherwise, let us conclude the session.
Uh,
So, I
okay.
would request Dr. Geeta to stop recording now, and we will be meeting again at 5 p.m. So 5 to 6 p.m. Dr. Sarthak Singhal would be taking on open related circuits. After that, I will be taking from 6 to 7 p.m. So thank you so much, Dr. Girdhar Gopal. You have
Thank you, ma'am. Thank
given
you.
good time to explain each and